Yeah, hi, this is Frank Owen, professor at Cal Poly Mechanical Engineering in the Mechanical Engineering Controls Lab. I want to show a problem that you can run into when running the Motomatic experiment, which is a common problem in industry when you're working with mechanical devices. The problem you have to deal with is friction. Actually, we call it stiction. So let's talk about this a little bit. I have the Motomatic set up to run in closed loop. Actually, it's all wired correctly, and I'm getting a signal from the feedback at this position here. I have this set on 4, as you can see, and that means with that set on 4 that the test meter is connected there. And I have the test meter, which is analog, hooked to a digital multimeter, so there's a reading there. I'm stealing this signal here. I'm stealing it from the test lead, which is connected over here to the Motomatic, and then sending it over into this first analog input on the left on this DAC card. Everything's turned on. You can see the lights on and everything. Okay, now I'm going to run that. Excuse the quality of this, I'm using a cell phone to do it. So I come up here and I click run, and I got to get ready because I got to put in my input when it starts to go, and I've captured my input there. Okay, now a problem with this is that you could just take this at face value and say, okay, that's what I have, but we have the stiction problem, and the stiction problem is this. The angle, this is a measure of voltage, but it indicates the angle that we jumped from to, and it looks like we jumped from a little bit below 0 to a little bit above 3. The problem, though, is that you have a stiction range in here that this can settle around. If we had no stiction, it might not actually settle in this spot. There's a range that you need to find that you really want to be in the middle of that range. And so we've come up with a way of dealing with that problem. So let me demonstrate that. What I'm going to do, and let me say a little bit more about that, I suppose, before we go forward. The signal that, the actuation signal that comes back depends upon how far off you are from the final value. And for instance, when we're down here, we have a big actuation signal that moves the Motomatic to a new position, and we come up here, and what we should see, since this is a second order signal, is we should see some swinging back and forth with a decreasing magnitude because it's a second order underdamped system. What happens, though, is when you get inside the stiction range, you may be close enough to the desired final value that you don't really have enough juice going back through the feedback loop to move this to the correct location, which would be the middle of that stiction range. So it just kind of gets stuck in this band, and we don't know whether the band is up high or down low, or it just by luck happens to be in the middle, and so we have this procedure for figuring that out. So what we're going to do is this. It's still clicked into the on position there, as you can see, but I come back to the Motomatic, and what I want to do is find the center of that range. So I'm going to come over here actually and turn my Motomatic in one direction or another, doesn't matter which one, until you start seeing it. See, I pull it and it springs back. So that's the end of one range. And we want to note that value. So that value is 2.152 or 3. And then we want to find the other end of that range. So we turn it in the other direction until we start getting some resistance back. And now I'm at the other end of the range, and I'm at 3.52 volts. So what that means is that the center of that stiction range is the average of those two values, so you can find that. You can do a little calculation and find that, and that's where it would wind up if there were no stiction. Now we turn it off, and we actually spring back to another position, Here in my voltage I have negative 0.486, but I don't know whether that's actually the center of the zero range. So we have the same problem at the bottom of the range that we had at the top of the range. So you do exactly the same thing again. You come here and you turn it in one direction until it starts to fight back. And I got, with that, 0.549876, it's 0.54 something or other. And then we turn it in the other direction until it starts springing back. We want to get it right on the edge of that. And when I do that, I get 0.799.8. So the average of those two values is the bottom of the stiction range. What this means is that you want to start off with it in the center of those two values. So before you do another run, what you need to do is calculate that value, and then you first come and you change this until it's in the center of that range. I don't remember the values, but I can actually kind of do it by hand too if I want to. If I look at where it is, and I notice that here I have a pin right here for this coupling in that position, and then I turn it down. Oh wow, it's gone way around, almost 180 degrees. So if I set that pin like halfway in between, I'm at 0.235 volts. I'm not sure, I need to actually calculate the values, but if I were doing it just by hand in a sort of Bakersfield type way, you know, you could do this. This is a rough way to do it. Actually, though, I think that this probably should be pretty close to zero, so you can simply come here and turn this and get it on zero or close to zero. Now we've gone the other direction. Oh, where's the negative sign? Okay, we're getting really close to zero here. So this would be a good place to start. And if I look up at this, I can't remember where the locations were. But anyway, what you should basically do is turn this until you get the center of those low values, and then you can start your experiment. You need to do that every time you do a step. Start off at the mid value of the lower stiction range. And then when you, so I'll just demonstrate it again. Let's say that this is the mid value. When I do my run, let's see, so I want to capture this and go back over to my DAC system. I run it again. This disappears down here. I wait for it to appear, and then I run it again. Oh, now see, I got very little overshoot there. So sometimes it gets captured at the bottom of the range, sometimes at the top of the range. But what you would do now is, like I said before, you would go back here and turn this in one direction until it fights back, record that value, turn it in the other direction until it fights back, record that value, and then the average of those two values is the midpoint of the stiction zone. And if you had no stiction, that mid value is where it would wind up. I hope this helps. It's better than no material on it. Sorry for the quality of the video. I'm doing this rather quickly because the lab's going to run for the first time tomorrow. Thanks for watching.
Before we ran this, what we should have done is had this value start at 0.127. This actually looks like it's not too bad. It's close enough. So when we run it, hang on one second, we jump up to a value that's pretty close to 4. But actually we determined before that the mean value of the stiction zone was 2.846. And that's actually what we should use as our final value after the step. If we don't do the procedure as discussed earlier in this video, what will happen if you use this higher value to calculate your overshoot, you're going to be completely wrong. So you'll come up with an overshoot that's small and a percent overshoot that's very small, and that will give you a good deal of damping, more damping than you actually have in the system. So it's important to follow this procedure and use in this case, the 2.8476 or whatever it was as the final value for the step, and then calculate your overshoot from that. That's the end of the video. Thanks for watching.